everyone. This is my first lecture on equilibrium, which is chapter 13, and chapter 16.8, which is from thermodynamics, but we're going to go back and pick up a little bit, which relates equilibrium to thermodynamics. And we're studying equilibrium, which is slightly different than what we have always thought about reactions, which is typically you will have this nice single-headed arrow, which implies that you've got reactants that will react with one another and form products, and it will go all the way from reactants to all the way to products, and then that's all you've got. That's true for some reactions, but actually a lot of reactions are in an equilibrium state in which you start with reactants and they will react together and they will form products. And then when the concentration of products gets high enough, they will start reacting with one another and going back the other direction to some extent. So you end up with concentrations of reactants and products being constant, and this double-headed arrow is a more accurate representation because you're reacting forwards and reacting backwards at the same time. And we are going to now go watch a YouTube video, which is only like a minute long. Come on. That describes this in more of a visual way. Are you ready, assistant?
Yes.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium where the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed in the breeze. This continues until the towel is dry and can be represented by a simple chemical equation. This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel. At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
So, what we learned from that video, which made me laugh, was that the reaction is flowing back and forth. You have reactants that are going to products and products that are going to reactants, forwards and backwards with the reaction. And the concentrations overall stay the same, but you do have flow in both directions. That is a state of equilibrium. And they were showing evaporation, but that's the case also for things that are actually reacting, where you start with different reactants versus products and they go left and right simultaneously. And they made the point that it's got to be in a closed system, because in an open system, you lose your products and they go away, and so they're not really available to go back and forth like they do in an equilibrium. So any reaction in a closed container will reach this equilibrium eventually. And what's interesting is that the particular equilibrium that you reach can be described as lying far to the right or lying far to the left. And what that means is if your equilibrium is on the right side, it means that you have a whole lot of products and relatively little reactants. You've still got flow going between the reactants and products and reactants, but most of it initially made it to products before you reach a state of equilibrium. If you have an equilibrium that's lying far to the left, it means that most of what you have is reactants, and there are barely any products that have been formed. So, you know, you set this thing up and you let it go and it goes, it makes a little bit of products. And then you've got back and forth flow between the products and the reactants, but not a lot of it ended up staying as products. You can also have a reaction that's pretty centered, where you've got reactants and products in relatively equal concentrations, reacting back and forth. But the thing to remember is that the reacting has not stopped. It's not like it gets to equilibrium and then freezes. You've always got this double-headed arrow showing that, you know, the reaction is continuing forward and continuing backward. And the metaphor that they use frequently is to think about if you've got two islands and a bridge, you can have the same population at all times on the islands with traffic crossing the bridge, as long as the traffic is in equal amounts. And that's a pretty good representation of an equilibrium system. The populations are static, but the individual people are moving back and forth across the bridge. All right, mathematically speaking, how to represent a particular equilibrium is to kind of show mathematically what the concentration of the products and the reactants are in the equilibrium. And the way that they do that is they will set up this really complicated fraction-y thing. And what's cool is that for any system, for any reaction at a particular temperature, when you set up this this equilibrium expression the way that you're supposed to, you will always end up with the same K, which the K is the equilibrium constant. And so that ends up being really significant when you're running the math on these equilibrium things, is that at a particular temperature, a particular system will always have the same K. No matter what concentrations of whatever you started with, it will get to a situation that will give you the same K. And so if you have just a generic reaction, here's to give you the idea of how to put together this equilibrium expression, which you will be doing a lot. If you've got reactant A and reactant B, and product C and product D, and then you've also got numbers that are your coefficients here for the balanced equation. It has to be balanced. If it's not balanced, you won't know what the numbers are. So there's F moles of A, G moles of B, H moles of C, and J moles of D. What you do is you put your products on top, your reactants on bottom, so you have C and D on top, A and B on bottom. And they are in their square brackets here. And if you remember, we've done this. Square brackets means concentration of. So this is the concentration of C, this is the concentration of D, concentration of A, concentration of B, and that's molarity. So big M, moles per liter. Sometimes they'll give you amounts and the number of liters of the container. You have to figure that one out. Typically they will give you the molarity, the concentration in molarity. So this is molarity of C, and then the coefficients end up being important because you've got the molarity of C raised to the power H. So if this were in the balanced equation, if it were 2 moles of C, this is the concentration of C squared. And if this were 3 moles of D, this would be the concentration of D cubed. Okay, so you do products over reactants, concentrations to the power of the number of moles. And that is how you do this. So for example, if you've got your really normal equation that we do a lot, here's our double-headed arrow, yay! Where you've got 2 moles of hydrogen, 1 mole of oxygen gas, and it's reacting back and forth, and you've got 2 moles of vapor, water vapor here. You have the products on top and the concentration, so the concentration of water in brackets, to the power of moles, so squared because of this 2. And then the hydrogen also squared in brackets because of this 2. And then oxygen just to the first power because it's got an invisible 1. So if you actually had numbers for these concentrations, you could stick them in to these spots and you would know the value of K. So I'm gonna be jumping back and forth to do some of the examples that I'm giving in these notes that need to be done in order for you to know what the heck is going on. And then the ones that I skip, we're going to do together in class. but I will have given you the document that has all of these examples from the Zoomdall book typed in for you, so we can do them together without having to bring our books to school. So 13 point, which one are we doing? Are we doing 13.1? We're doing 13.1 and 13.2, just A and B. Nope, that's YouTube. There it is. All right, so, and we need a pen. It needs to be white. White pen. Did it work? Yes. Okay, so it says, write the equilibrium expression for the following reaction. We have 4 moles of ammonia gas and 7 moles of oxygen gas, and your equilibrium double-headed arrow, so giving you 4 moles of nitrogen dioxide gas and 6 moles of water gas. And the way you write this equilibrium expression is you've got K, which is your equilibrium constant. Frequently they will have a little C here, which represents that this is the K that you get when you're using concentrations. That's what that C is. Often they will leave the C off because they figure that you know that. So K is the same thing as Kc. And you've got to have your products on top in brackets. So we've got to have the concentration of nitrogen dioxide, and to which power? 4 to the 4th power, times the concentration of water to the 6th power. And remember again, we've got to have our products on top and our reactants on bottom. So our reactants are going to be ammonia gas to the 4th power, and then whatever the concentration of oxygen is to the 7th power. And that would be fun to type into your calculator. That's the structure of putting together the equilibrium expression in order to get your equilibrium constant. And then I think the next thing that I do is 13.2. So here we go with 13.2. Here we are with actual numbers. We're going to make that equilibrium expression and put actual numbers in. Woo! All right. The following equilibrium concentrations were observed for the Haber process at 127 degrees Celsius. One thing that you need to know is that the Haber process is like the main reaction that they ever talk about with equilibrium. So you should probably know it. And the Haber process is how to make ammonia. So nitrogen and hydrogen gives you ammonia, and you got to balance that sucker. So that's 2 and 3. Yeah. And they're all gases. We'll learn in a little bit that gases and aqueous solutions work because you can have concentrations of them, but not so much with a pure liquid or a pure solid, because what is the concentration of a solid? You don't know. So these gases, the following concentrations were observed for this. So the concentration of ammonia is 3.1 E negative 2 molar. Concentration of nitrogen is 8.5 E negative 1 molar, and the concentration of hydrogen is 3.1 E negative 3 molar. And it says calculate the value of K at 127 degrees for this reaction. So we set up our equilibrium expression equal to our equilibrium constant. Our equilibrium expression is squared over nitrogen by himself and hydrogen cubed, and that's going to be and then you've got 3.1 E negative 2, and now you use regular parentheses because you've put the numbers in, by the way, squared divided by 8.5 E negative 1 and 3.1 E negative 3 cubed. And I'd like to make a point about how you put this in your calculator, because this is going to come up. It's hard to get all this into your calculator at one go, and I wouldn't recommend doing that, honestly. I would go 3.1 E negative 2, enter. Squared, enter. Divided by 8.5 E negative 1, enter. Divided by 3.1 E negative 3 cubed, enter. And that was important because it's the top number divided by the two bottom numbers. You're going to be tempted to do if this were a squared over b times c cubed. You're going to be tempted to do a squared divided by b times c cubed. You can't do that because you didn't put the parentheses in inherently when you do that in your calculator. What you've got to do instead is type that in this fashion, which is a squared divided by b, enter, divided by c cubed. Okay, remember that because I bet you're going to make that mistake a bunch. Don't do that. So there you are. So you type that in, and I've already done this ahead of time, and so you get back out I'm apparently moving the whole screen when I use my pen, 3.8 e to the fourth. And that is your answer. And what's interesting is that k does not have units. But it could have units. Yeah, but they kind of decided to bail on units, and they're like, we're just not going to deal with units for k.
Yes.
So when sometimes you'll see a question that will say, you know, make sure you do k and put its units, and you're supposed to say, here's k, but there are no units for k. Take that. So don't forget. No units for k. It's kind of nice because you're always tempted not to put units, and you're actually right this one time. All right, so calculate the value of the equilibrium constant for this reaction. Now this is interesting because A and B. Oh, this goes back to 3 bits to know about k in math, so I need to do a little bit more lecturing here. The thing about k, mathematically speaking, we've got 3 little bits to know. We know how to find a regular k. If you have written the reaction in this direction from oxygen and hydrogen to water, if you actually just flip it and go from water to hydrogen and oxygen, you don't really have to redo the entire equilibrium expression math stuff, because what you've got here is products over reactants. If you flip it over, all you've done is reactants over products. And so you can actually just take your number and flip it over, 1 over that answer. Or you can use the little to the -1 power button that you have on your calculator. So a reversed reaction has a reciprocal for the k. So that's important because they'll often say, calculate this k. Now what would it be if you flipped it backwards? And you're like, well, you just flip it over. Right, the second one, if you have a multiplied reaction, so for example, if instead somebody writes this as 4 H2 and 2 O2 yields 4 H2O, if you've multiplied the entire thing by 2, what that does is that changes your exponents, right? It raises the original k to that power. It's like taking this and squaring the whole thing. So if you've doubled the equation, you square k. So those are 2 things. It just makes sense the way the math works if you're being good with your algebra. So yes, ta-da. And then here's that other point. K has no units. They would be too crazy anyway, and there actually is some crazy math that they all cancel anyway, which we don't have to go into because we would have to have already done the kinetics unit, and that's not till next semester, and anyway, it's terrible. So they just kind of went, no units.
Yes.
Yay. So you get back here and you get to 13.2b, and you have a C on your paper, by the way, which you should do on your own. And here's an example. Calculate the value of the equilibrium constant for this reaction. Well, if you look at it, this is ammonia that yields nitrogen and hydrogen. That's the flip of this reaction up here, the Haber process. That's taking ammonia and breaking it down into nitrogen and hydrogen. But since this is equilibrium anyway, and it's going forwards and backwards simultaneously, and it reaches an equilibrium position no matter how direction you write it, it doesn't really matter. You just flip the number over. So this is 1 over 3.8 e to the 4, which in your calculator you can also do by 3.8 e to the 4 to the -1st power. And you end up with 2.6 e to the -5. That's your answer for B. And then C is a multiplying one, and you can figure it out. All right, ¿qué más? Here we go. there's a concept of the equilibrium constant and the equilibrium position. You can, what's interesting is that if you're at the same temperature for a particular reaction, you always get the same K. Even if you have different amounts of stuff overall, there's just a natural tendency for it to go to this kind of ratio. And so the equilibrium position is, versus the equilibrium constant, it's kind of like, you know, you can have a lot of different fractions that get you to 0.5, right? You can have a half, you can have 2/4, you can have 3/6. There are a lot of different ways that can get, there are a lot of different ratios that actually end up being 0.5. So in this metaphor here, K is your 0.5. That's your actual numerical answer. There are a lot of different amounts that you can have that would give you that same answer. So, you know, you might have, you know, 20 out of 40 that would give you 0.5. It's a little more complicated because your fraction in this case, when you're actually doing the K, has exponents in it. But there are a lot of different ways. If you had it, for real, if you had a K of, say, a half, can you think of more than one way of getting a half out of some fraction that has exponents in it?
To the 1 or 5 to the 1 over 10 to the 1.
So 5 to the first over 10 to the first. That's a good one. Okay. Now, what about if you had 6 squared?
12 to the 4th.
Ooh, no, that would be way too big. What is 6 squared?
36.
Okay, and so what do you need on bottom?
36 times 2.
Which is 72. So you could just have 72 to the first on bottom, or you could have, 72 isn't a nice square. So if we start using 2's, let's flip to our black pen here. So we can have 0.5 equal to, if you had, say, 2 cubed, that's 2 times 2 times 2, that gives you 8. So what do you need to have on the bottom?
16.
16. And there's actually a couple of different ways you can get 16. You could have plain old 16, or you could have 2 cubed over
2 to the 4th.
2 to the 4th. Or you could have 2 cubed over 4 squared. So there's a lot of different, and these are equilibrium positions because these are the concentrations, the 2 and the 16. You could have a concentration of, say, 2 and 16. There's just mathematically, there's a lot of different ways to get to 0.5. But you always end up with 0.5. So there. So it is crucial to know that for a given reaction at a given temperature, the K is constant, but the equilibrium position is not. There are a lot of different sets of concentrations that will mathematically result in the same K. And we need to now look at table 13.1, which I have hidden in, come on, here. Table 13.1 is here. So results of 3 experiments for the reaction, that Haber process that we were just talking about. You can have equilibrium concentrations of 0.921, 0.763, and 0.157. And that will give you a K of 6.02 e to the negative 2. You can also have equilibrium concentrations that are bigger than that. You can have 0.399, 1.197, and 0.203. And when you put those into this expression, you end up with 6.02 e to the negative 2. It's got to be at the same temperature to have the same K. You can also have even bigger concentrations. You can have N of 2.59, H of 2.77, and an NH3 of 1.82. If it's at the same temperature for this same reaction, you're going to get a K of 6.02 10 to the negative 2. So this is showing here are 3 different equilibrium sets, equilibrium positions that still result in the same K. And they're also trying to show you that you can start from, you can load this thing from the left or from the right. You can give, you can put into your container only reactants and it will go and end up with that K. Or you can put into your container only products and it will go and end up with that K. Or you can put in a mixture of reactants and products and it will go and give you the same K as long as it's the same temperature and the same reaction. So there we go. That's that. And now we get to do example 13.3. 13 point... No, we don't. We're skipping 13.3. 13 point... What does 13.3 say? Oh, but I want to do 13.3. We'll do 13.3 in class. I think this is proving to you that you end up with the same K when you do it two different ways. Two different sets of equilibrium positions. Yep. All right. We're not doing 13.3. We're going to keep going. But I just really love that question. I know, but we'll do it together later. All right. So we've been doing concentrations. That's your K, C, or just your plain old K. Pressures work too.
Oh, no.
I know, right?
Oh, no.
If you have a system that's all gases, the concentration of the gases is mathematically related to the pressures of the gases. So you will sometimes be given pressures, and you can just go ahead and stick those pressures straight into your equilibrium expression. They want you to write it with P's, though.
Oh.
I know, right? So let's go... and it ends up being exactly the same structure. Products raised to their exponents over reactants raised to their exponents. So let's go do 13.4. So the reaction for the formation for nitrosyl chloride, I know, right? NOCl. So 2 nitrogen monoxides plus chlorine gas gives you 2 nitrosyl chlorides. Was studied at 25 degrees Celsius, and the pressures at equilibrium were found to be 1.2 atmospheres for our product and 5.0 E negative 2, 3.0 E negative 1 atmospheres for our reactants. Calculate the value of K sub P. In this case, it's important to put the P for this reaction at 25 degrees Celsius. The structure ends up being exactly the same. The math ends up being exactly the same. You just have to remember in your head that this is a pressure-y one. So K sub P, this is your equilibrium constant with pressures, is equal to your products, NOCl, the concentration of your products, and we've got to square that guy, divided by your reactants, squared, and nitrogen. So that's going to be, where's our NOCl? 1.2. Oh, yeah, hey, chlorine is important. I have an eraser. Is it going to work? That's going to make it whiter. Wheel. How about black? Does that work? Yes.
Hey.
Now I have a black eraser. Take that. And now I think I have a black pen too. No.
Dude,
Chlorine.
that's great.
Okay. So, thank you for pointing that out, assistant. So, now we put them in. So, NOCl is 1.2 regular parentheses squared over, nice squiggle.
You could erase it.
I don't know if I can. Can I? I can. Yes.
I'm such a good assistant.
You're such a good assistant. Over 5, come on hand, 5.0 E negative 2 squared times 3.0 E negative 1. Okay, you stick that sucker into your calculator, 1.2 squared divided by 5.0 E negative 2 squared divided by 3.0 E negative 1, and you end up with 1.9 E to the third. And again, there's no units, even though this is Kp. That is your value for Kp for this reaction. Yay! Alright. Now, there is a relationship, there's a mathematical relationship, like I said, between concentrations and pressures. Because of that, you can convert between Kps and Kcs using this thing, which looks strangely familiar. It's got sort of a structure similar to the ideal gas law, because they basically took the ideal gas law and kind of crammed it down into the mathematical similarities between pressures and concentrations here. So that's where you get your R and your T and your N and na. Anyway.
They use a hammer.
Do they use a hammer?
We're going to go with yes.
They used a hammer. Yeah, I was like, I'm not seeing a hammer there, assistant. All right, how to convert between them. You use some constants. There's the constant R, which, if we remember, that's the ideal gas constant. It's 0.08206. And then your temperature in kelvins. And then your delta N, which I think we've seen that somewhere before. It's the change in the number of moles of gas. And it's products minus reactants, your typical end minus start. So example 13.5, we can go do one of these. Using the value of Kp obtained from 13.4, bing, calculate the value of K at 25 degrees Celsius for this reaction. So our Kp is 1.9 E3. So what we've got here is Kp equals K. I'm doing that right? Yeah. Kc times RT delta N. So the change in the number of moles of gas, we're going to need that for this N, so we'll go ahead and do that. How many moles of gas do we have in our products? 2. How many moles of gas do we have in our reactants?
3.
2 minus 3 is -1. So that's our N. Or delta N, actually. So our Kp, which we know, is 1.9 E3 equals Kc times 0.08206 times temperature in Kelvin, which is 273 plus 25, so 298 to the negative first power. That means you're going to have to find this number and then divide this by it. Algebra. So Kc equals, what did I get? 4.6 E4. Alright, so our Kp is 1.9 E3. When you do it with concentrations, it's 4.6 E4. This equation is just showing us there's kind of a simple mathematical relationship between our concentrations and pressures. Okay. Alright, what about solids and liquids? I mentioned this before. If you've got aqueous solutions, your concentrations work, right? You can have concentrations in, this is 2 molar hydrochloric acid. That works. It's gorgeous. And gases, you can have concentrations of gases because, I have 2 moles of gas and it's in a 2-liter container and it's 1 molar. You can also have pressures for gases. So you can do K for aqueous solutions and for gases. If you have a pure liquid, like if you have got pure water, and you're going, my reactant is water, what is the concentration of water? What does that even mean? You can't use a pure liquid in a K in an equilibrium expression. If you've got a solid, if you've got like a block of sugar, what is its concentration? All? Like, it's not a thing. So what ends up happening is if you have a solid or a pure liquid, which is often just H2OL, if it's H2OG, then you can use it. But if it's H2OL, then you can't. You just leave them out. This is called a heterogeneous equilibrium because it's heterogeneous in the sense that, you've got some gases and some solids or some gases and some liquids. So it's not all the same phase. Okay, you just leave them out because you can't have concentrations or pressures. It's kind of nice. It makes it easy. And I'm skipping 13.6? Yeah, I'm skipping 13.6 for right now. We can do that together in class. It's sort of easy because how hard is it to not put something in? You just have to notice that it says L or S, and then you don't put it in. And sometimes you'll end up with an equilibrium expression that has only got a top. Because your reactants are all solids. So that's okay. It doesn't have to be in a fraction-y form if there's only one thing in it. All right. Now that we've gotten through all of this and how to do it neener, why do we care about K?
Uh-oh.
What? why do we care about K? Why do we care about equilibrium and what, like, we can do all this math for it, but the reason that we care is because if you know K and then you do a little bit more, oh boy, you can figure out, well, if I put this in here, will it make products or not? Because, you know, maybe you're thinking, you're looking at this reaction that's written out and you're like, oh yeah, it's going to go to products, it'll be great. Well, what if your equilibrium lies really far to the left? You're going to put these reactants in there and go, and it will just sit there mostly being reactants. You're like, if only I could have some products. So you care about K because knowledge of K allows you to predict whether your goals of making products will be met or not. Because, you know, you can try putting stuff in there and just kind of go. And it's like, sorry, bud, my equilibrium lies far to the left. It's not going to happen. You're like, oh. Now, do you remember what I said? If you know K and you do a little bit more, here's a little bit more. K has a twin brother. His name is Q.
It's not anywhere near K.
Shh. It makes a K sound.
No. Fraternal twins.
I know. Okay. He's got a twin brother, Q, and this is called the reaction quotient. The good news is that you calculate it exactly the same as you calculate K. You just use different numbers in there. K, you're putting the equilibrium concentrations into the little fractiony thing. For Q, you're putting the initial concentrations into the fractiony thing. And then you can compare them. You can say, if I'm at equilibrium, it's going to be like this, like K. Right now, at the beginning, I'm like this, like Q. Is that at equilibrium? Is it gonna go? So you've got to calculate Q and calculate K, and then you can go, oh, Q is larger than K. I see. So here we go. Here's an example. We've got N2O4, dinitrogen tetroxide, going to NO2, which is nitrogen dioxide. And this is basically it splitting in half and making 2 moles of gas here and 1 mole of... I should have gases on here because you have to have gases. If at equilibrium at 600 K, for example, you know that your K is 2. I made it a pretty easy number for you.
Well done.
If you know that your K is 2, then we would like to know what will happen if we put these things into a glass container. Which way will they go? Will I end up with more products or more reactants or what as they move? So we've got a concentration. We put in 3 molar nitrogen dioxide and we put in 3 molar dinitrogen tetroxide. This is my first option here. This is my first scenario. Question is, what is Q? So you do Q equals the concentration of NO. This is going to be amazing, guys. 2 squared over N2O4, right? He put it back. So that's going to be NO2, which is 3. So we're going to have 3 squared over 3. I know, right? That's going to be 9 over 3. That's 3. So if Q is 3 and K is 2, that means putting 3 molar NO2 in and 3 molar N2O4 in is not at equilibrium. Because at equilibrium you get the answer 2. We are not currently at equilibrium. We're at 3. When you have this answer 3 and you compare it to 2, Q is greater than K. But you can't tell because it keeps eating my sign. Q is greater than K. If Q is greater than K, and you have to think about fractiony things here, that means that in this Q expression, the top is too big.
Okay.
Right?
Okay.
That's what's making Q bigger than K. The top is too big. That means we need less top.
Okay.
Top is products. So that means in order to get from the situation that is represented by Q to the situation that is represented by K, it is going to move so that there will be fewer products going from the products to the reactants. And that's shifting left. And so that's important. So what happens? It shifts left. So in a situation in which Q is greater than K, your top is too big. To fix that, it goes left. That is true every time Q is greater than K. So it might be helpful to memorize that when Q is greater than K, it goes left, because if you don't memorize that, you're going to have to think about the dang fractions every time. Okay, if Q is greater than K, that means that there's... Wait, what does that mean? Q is greater than K, it goes left. Okay, so let's do this one. Your initial is 2 molar NO2 and 4 molar N2O4. So Q equals 2 squared and over 4. So you end up with 4 over 4 or 1. Aha!
Aha.
Aha!
Aha.
So in this case, Q is less than K. I bet you could have guessed that that would be the next one. So in the situation in which Q is less than K, Q is less than K because your top is too small. Your top is your products. That means we need more products. And so when this situation goes to equilibrium, it's going to make more products. Because it's going to equilibrium. It's going to go. You just want to know, well, which way is the going going to be? Left or right? The answer is you've got to have more products, it's going to go right. So in this case, it's going to go, it shifts right. It's maybe helpful to memorize that when Q is less than K, it will shift right. All right, next. Can you guess what this one will be?
The same.
Shh, don't tell though. Okay, so in this situation, you've got Q, your NO2, which goes on top, is 6 squared over 18. What's 6 squared?
36.
And what is 36 over 18?
2.
2. So when Q is 2 and K is 2, my goodness, look at that. Q equals K. So we, unbeknownst to us, put in 6 molar nitrogen dioxide and 18 molar dinitrogen tetroxide, and we're like, which way is it going to go?
No way.
It's not going to go. It's going to stay that way because your Q is 2 and your K is 2. When K is 2, that's at equilibrium. We accidentally put the stuff in already in an equilibrium position.
Good for us.
I know, we're very fancy. Nothing. It stays in that situation. You're gonna put that stuff in and wait for it to change, and it's gonna stay 6 molar NO2, 18 molar N2O4.
It's fancy.
And do I have another problem? I do have another problem to do. Okay. Sorry, this is getting long, isn't it? It's so long, Mrs. Gunlock. I know, right? All right, 13.7. For the synthesis of ammonia, the Haber process. At 500 degrees Celsius, the equilibrium constant is 6.0 e to the negative 2. Predict the direction in which the system will shift to reach equilibrium in each of the following cases. All right, so here, this is basically the same thing, but with real numbers instead of 2 and 3. Oh, boo. So we've got K, and that's going to be, this is this reaction again. Do I have to memorize that reaction? I don't really see how you can avoid memorizing it the number of times that they make you do it. But yes. So that's going to be NH3 squared. Don't forget your brackets. Okay. And nitrogen and hydrogen cubed. So that's going to be 1 e to the negative 3 squared over 1 e to the negative 5 times 2 e to the negative 3 cubed. So that's going to be 1 e to the negative 3 squared divided by 1 e to the negative 5 divided by 2 e to the negative 3 cubed. And you're going to end up with some number. What is it? 1.25. So 1.3 e to the 7th. Now, that's K. No. No, that's not K. Don't be silly. That's Q. That's our current situation. This is our current situation. I know that you've been all sitting there going, I thought it was Q. What's wrong with me? Nothing. It's me. This is Q. Our Q is 1.3 e to the 7. Our K is, what is our K? 6.0 e to the negative 2. Which one is bigger?
Q.
Q is bigger, so Q is greater than K. Which way is it going to go?
Left.
Is it going to go left? It's going to go left. Because Q is greater than K. That means our top is too big. That means our products are too big. And so it's going to go towards reactants, which is left. So this is going to go left. Big letter L. Bam. And B, we do the same thing. Is this one going to be the other direction? Probably. I wouldn't really have given you an example that was exactly the same, do you think?
Well, but that would be fun, though.
Maybe. Why did you change your brackets? Shh. And you get, which one is this? The 2 is it? I get 6.0 e to the negative 2.
What did you do?
It's the same number. So, again, we accidentally put in precisely the correct amounts to already be at equilibrium. It's not going anywhere.
Pretty constantly
I
amazing.
know, right? And for C, we will do that in class. And now I think our last example is 13.9. At a certain temperature, a 1.00 liter flask initially contained 0.298 moles of PCl3 and 8.7 e negative 3 moles of PCl5. After the system had reached equilibrium, 2.00 e to negative 3 moles of chlorine was found in the flask. Gaseous PLC5 decomposes like this. So PCl5 gives you PCl3 and chlorine. Calculate the equilibrium concentrations of all species and the value of K.
Oh boy.
This one is rough. There is a tool. It is called an ice chart. I'm going to introduce you to this chart. It is going to be your friend for about the next 3 months.
Friend or enemy?
Shh, shh, shh.
Oh boy.
Don't insult the ice chart. The ice chart will seek its revenge. Alright. Phosphorus pentachloride, phosphorus trichloride, and some what's that? And some chlorine. You draw a chart. You write ice. Why do we write ice? Because the I stands for the initial concentration. The E stands for the equilibrium concentration. The C stands for the amount of change. So initial, change, equilibrium. You put in as many numbers as you know. What we know is initially it's a 1 liter flask, which is very thoughtful. That means we don't have to change these numbers because it's 0.298 moles per 1 liter. 0.298 moles of PCl3. So that's 0.298 molar, right?
Right.
And 8.7 e to the negative 3 moles of PCl5. So that's 8.7 e to the negative 3 molar. That's all it contained. Okay? I didn't put in any chlorine. There's no chlorine initially.
Okay.
Okay. After the system had reached equilibrium, 2.00 moles of chlorine was found. Oh my goodness. That's this. 2.00 e to the negative 3 molar was found in the flask. So, we put in these two things. There was no chlorine. We're not sure how much of these there are at equilibrium. But one thing that we can see is that chlorine changed from nothing to something. So which direction did it shift?
Right.
It went right. Some more of this decomposed and you got some chlorine. How much decomposed? This much.
Not much.
Yeah. So it's 0 plus some amount, and you end up with this. Well, it turns out that X is equal to 2.00 e to the negative 3 molar, right?
Right.
It shifted right. So we lost some of this. How much did we lose?
X.
This much, X. So this is actually the change is minus x. And did we gain any PCl3?
Yes.
How much?
X.
X plus x. Because this is all 1 molar, 1 molar, 1 molar. If this had been 2 molar, that would be plus 2x. Because you get twice as much as, but it's not. So we lost some of this and we gained the same amount of each of these. We already know what x is. Isn't that nice?
Yes.
It is nice because later you have to figure it out using the quadratic equation.
Oh.
Yeah, you love that, don't you? But they told us, look, they told us what x is. So this is 0.298 plus this, which, by the way, is 0.002. What's 0.298 plus 0.002?
3.3.
0.3 molar. And what is 0.00873 minus 0.002?
0.00673.
Yeah. Bam. There are our equilibrium concentrations. Now let's do K.
Oh.
There's more. Oh, wait, guys, this is a short one. Oh, we're going to die. Yeah, probably. Don't tell us that. Why not? Now, what numbers should I put in here?
Equilibrium numbers.
Yes, because K is the equilibrium constant. If I had been mean, I could have made you calculate Q, too.
Are you mean?
You're not being mean? It looks like you're being mean. Shh. 0.002
That comes later.
times 0.3 divided by 0.00673, and that equals 0.0896.
What units is that?
No units at all.
Yes.
All right. Woo! Thanks, folks. See you in class.